Yeah, I can hear you. All right. Well, let me start by saying thanks a lot to the organizers for the invitation. I'm very sorry I couldn't be there in person, so this will have to do for now. But it looks like there have been some really interesting talks so far. Great. So today I'll tell you about this project that appeared a few months ago in some work in progress together with Lorenz Eberhardt and Mengyang Zhang, who's a grad student at Princeton. I hope this talk is not too much of a non sequitur in the program here, but 3D gravity is always at least number theory adjacent. So let's get started. Um, so in many recent approaches to quantum gravity, a sort of central figure has been this Euclidean gravitational path integral. So what do we do in quantum gravity? We integrate over dynamical metrics, gauged by diffeomorphisms, and some over topologies. But I want to emphasize that in most situations, we don't really know what the rules of the game are with this thing. And in many cases, the rules are sort of made up in an ad hoc way as we go. Um, so questions that one might have about this object that could be relevant are, what topologies or geometries should even in principle be included in this sum over topologies? Do we allow singularities? When is the saddle point approximation valid? How do you go beyond the semi-classical saddle point expansion? What about off-shell configurations in gravity? So it would be nice to have a setting where we could sort of answer these questions more precisely. And you might think that string theory would be a good setting for that, but certainly I think it's fair to say that as presently formulated and understood, string theory is typically not well suited to these sorts of non-perturbative questions that involve sums over topologies, for example. So one might perhaps naively hope that it would be possible to retreat a little bit from string theory. And in particular, you might wonder whether it's possible to sort of isolate the essential physics. After all, string theory includes many perhaps unfamiliar ingredients from the point of view of semi-classical gravity, and consistently formulate a simple theory, something like pure quantum gravity. Now, in this case, the boundary holographic quantum system would in principle describe the physics of gravitons in black hole microstates. So if one could make this precise, it would provide an extremely appealing and clean theoretical laboratory in which one could ask very fundamental questions about quantum gravity and quantum aspects of black holes very precisely. I should emphasize that this might not be possible. In fact, there's good reason for skepticism about this. However, even if not, along the way, we might learn something about the minimal set of ingredients that are needed in order to consistently formulate quantum gravity. And you might be able to bootstrap yourself up to something like something like the conclusion that string theory is the only game in town. And moreover, these situations with simple theories of quantum gravity in the bulk, they may lead to slightly modified or more what Collier and Jensen called mesoscopic holographic paradigms, where the boundary theory is perhaps not a particular complicated quantum system, but some statistical ensemble of quantum systems that captures the statistics of UV-complete boundary theories. Now, in recent years, I'm sure everyone in this room is aware, theories that are almost pure theories of gravity in 2D quantum gravity have received a lot of attention in recent years. And the most famous example is Jakob-Teitelbaum gravity and deformations thereof. So Jakob-Teitelbaum gravity is a theory of a dilaton and a 2D metric. So it has this slightly modified Einstein-Hilbert term with phi times r plus 2. And the reason this theory is so solvable is that you can integrate out phi, and this sets r equals minus 2. So this is essentially a theory of hyperbolic topologies in 2D. In this theory, it's not just some toy model that we like to study. It does, and not just JT gravity, but more general theories of 2D dilaton gravity arise universally in the near extremal limit of higher dimensional black holes. And importantly, as was shown in an important paper by Saad Shenker and Stanford in 2019, the holographic dual is not a particular quantum system. Rather, it's a double-scaled random matrix integral, which is rather a statistical ensemble of boundary Hamiltonians. we go. Now, in going up in dimensions, it's, I think, fair to say that perhaps the next simplest theory of gravity would be three-dimensional Einstein gravity with negative cosmological constant. And you can imagine coupling this to very massive point particles as well. So here we just have the Einstein-Hilbert term. Now, you might expect that this theory is actually completely trivial and not interesting to study at all. And the reason for this is that all solutions are locally identical. They can be written as discrete quotients of hyperbolic 3 space. And indeed, there are no propagating gravitational degrees of freedom. So in a local sense, it kind of is trivial. There are no gravitational waves in this theory. But it's really not trivial. The theory has a rich structure of boundary gravitational dynamics, which you can think of as gravitational analogs of edge modes of some quantum Hall system. And these boundary modes, in fact, it's well known, generate an infinite dimensional asymptotic symmetry algebra, which is the Virasoro algebra, infinite conformal symmetry of 2D CFTs, with central charge related to the ADS length L and the Newton's constant in the way that Brown and Hinault told us in 1986. And I think most importantly, this theory is known to support non-trivial black hole solutions, and this is ultimately our real interest, the reason for our real interest in the theory. So as a holographer, it behooves us to ask ourselves, what exactly would it mean to solve this theory? The conventional wisdom would be to simply construct the dual 2D conformal field theory, ideally a large C family of such theories. Now, what does it mean to construct the dual 2D CFT? Well, CFTs are completely solved at the local level in terms of their CFT data. So this is given by some spectrum of their local operators, particularly the primary operators, which are labeled by two quantum numbers H and H bar. So that's one ingredient that you need to solve the theory. The other is the dynamics of those local primary operators, their structure constants or 3-point functions on the sphere. So what would a 2D CFT dual to something like pure ADS3 gravity look like? Well, here's a rough cartoon of such a spectrum. You have, so here's a plot of H plus H bar. At 0, you have empty vacuum ADS3. And then if the theory only has black holes in the bulk, then you expect a large gap in the primary operator spectrum until roughly C over 12, which is this black hole threshold. And then all of a sudden the spectrum becomes exponentially dense and, in a rather precise sense, chaotic. So what you could ask is whether this kind of spectrum that I've sketched here is consistent with basic CFT axioms. And despite a sort of significant body of work that's been done to carve out the space of possibilities, particularly in this holographic regime, I think it's fair to say that basically nothing close to this kind of CFT has actually been constructed. But of course, it hasn't been ruled out either. Now, what are further hints about how to construct this theory? And that one can obtain many hints about the UV details of this theory from the low energy effective theory. So for one thing, black holes are famously characterized by a Bekenstein-Hawking entropy. And as Gibbons and Hawking told us, this entropy can be computed in the low energy effective theory from the Euclidean black hole saddle in the gravitational path integral. So we interpret this black hole entropy as a hint from the low energy effective theory about some coarse-grained statistical details of the microscopic UV completion, as shown in explicit detail by Strominger and Vafa in 1996, and argued on more general grounds by Strominger in 1997. So it tells us about some coarse-grained density of states in this black hole region. But there's more. We have more from semi-classical gravity than just the Euclidean black hole. ADS3 gravity is also known to admit multi-boundary Euclidean wormholes as bona fide actual solutions of Einstein's equations. So here's an example. Consider a topology that is equivalent to sigma, where sigma is some Riemann surface times an interval. And in some situations, you can in fact write down very explicitly the metric on this Euclidean wormhole saddle. Here, d sigma squared is the hyperbolic metric on the boundary, and rho is a coordinate along the wormhole. These are, of course, conceptually puzzling from the point of view of the traditional, conventional holographic paradigm, because these non-factorizing contributions to the gravity path integral are at least naively inconsistent with the holographic dual being a single boundary quantum system. But let's take them at face value and see where they lead us. So our point of view is that one can view Euclidean wormholes as providing a low energy window into the UV completion in the exact same sense as black hole entropy, in the sense that we view them as encoding coarse-grained statistical details of the space of holographic CFTs. So for example, consider the two-boundary wormhole where each boundary is a three-punctured sphere, and you have three heavy defects propagating through the wormhole. You can compute the on-shell action of this Euclidean wormhole and interpret it as defining the variance in some statistical ensemble of structure constants. So in this paper from 2022 with Jivan Chandra, Tom Hartman, and Alex Maloney, we computed the on-shell action of this wormhole, got some very explicit answer, and interpreted it as a statistical variance of the structure constants. In fact, for the experts, the answer we found is simply related to the DOZZ formula of Liouville CFT. Now, more provocatively, one could try to interpret these wormholes as computing averaged CFT quantities in a putative ensemble holographic dual. And to try and take this idea seriously and see how far we can get with it, consider some maximally random ansatz for the CFT data that we called the Virasoro eigenstate thermalization hypothesis. So you can consider some random ansatz for the CFT data where the OPE coefficients C are given by the square root of this variance, this DOZZ formula that computes the on-shell action of this wormhole up here, multiplied by some random tensor with Gaussian statistics. So they, for example, average to 0, but the average of the square is given by this variance. And indeed, what we showed in this paper from last year is that averaged CFT quantities in this Gaussian ensemble of CFT data precisely reproduce on-shell actions and often one-loop determinants in semi-classical ADS3 gravity. So returning to this wormhole, this two-boundary genus 2 wormhole that I sketched at the beginning, we showed that, for example, this computes the averaged product of genus 2 partition functions in the CFT in this Gaussian ensemble. But let me emphasize that although this works at the level of on-shell actions of individual topologies, this really cannot be the full story. And there's a really important difference from this JT RMT duality in higher dimensions, which is locality of the boundary theory, which is particularly sharp for CFTs. So the boundary theory is subject to an infinite set of non-perturbative consistency conditions, which amount to locality, or sometimes referred to as crossing symmetry or modular invariance. And there are actually large violations of this in this Gaussian ensemble, and this was emphasized in a recent paper by Bellin and collaborators. So although this ensemble is crossing invariant on average, for example, the variance of the crossing equation could become very large. It is not under parametric control. And more conceptually, while we have this sort of phenomenological ensemble of CFT data, it's not really clear even in principle how one should properly define an ensemble of CFTs or some more general notion of random CFT, how this should even in principle be defined in the absence of a conformal manifold. And conceptually, you might think that there's some tension between this extremely rigid structure of the boundary theory and expectations from quantum chaos in the bulk. So making this precise is an important goal, and there was a recent paper, again, by Bellin and collaborators that went a bit further in trying to make this precise. So all of this was to motivate the question, can we make sense of the bulk theory in its own right, from its own point of view? So one of the messages of what I've told you so far is that the dual of pure ADS-3 gravity, the status of this is very much unresolved and up in the air, although I think there has been some very interesting progress made in recent years. Now, returning to the bulk theory, as I said at the beginning, although it's not trivial, it behaves in many ways like a topological theory. For example, through this absence of bulk propagating degrees of freedom and the edge modes and the characterization by the edge modes. So at least at the level of individual topologies, topological quantum field theory, or TQFT, thus provides a very natural framework in which to study this theory exactly. So today, for the rest of the talk, I'll return to the bulk, and we'll discuss the canonical quantization of the theory, and what follows, I'll concretely relate it to a novel TQFT, which we call Virasoro TQFT. And if there's one thing I want you to take away from this talk, it's that this reformulation is more than some abstract nonsense. It's actually quite explicit and can be extremely useful. And I'll argue that it completely solves 3D gravity, at least at the level of fixed on-shell topologies. So that's very nice, but it means that puzzles having to do with A, the sum over topologies that appeared in the gravitational path integral at the beginning, and also the contributions of off-shell configurations are still basically at large. So to sketch out a plan for the remainder of the talk, I will discuss the gravity phase space and its relation to SL2R Chern-Simons theory. I will then discuss the quantization of that phase space, which is related to the quantization of the Teichmuller space of Riemann surfaces. And we'll then introduce this Virasoro TQFT, and we'll discuss some properties of this theory. I will then describe how to compute 3D gravity partition functions, and we'll both sort of lay out the general procedure, how this works in practice, and we'll try to illustrate that procedure with some examples. Before going on, let me ask, are there any questions? Okay, if not, I will continue then. So it's been known since the olden times that ADS-3 gravity admits a classical reformulation, at least in the first order formulation, first order formalism, in terms of a topological gauge theory, in particular, 2 copies of SL2R's Chern-Simons theory. Why do I say that? Well, in the first order formalism, in gravity, the gravitational variables are the Vielbein and the spin connection. Now in 3D, you also have the Levi-Civita tensors, so you can dualize the spin connection. You consider this object with 1 Lorentz index and 1 spacetime index. Now you can combine these gravitational variables. Here L is the ADS length that appeared at the beginning, into 2 SL2R gauge fields. And why do I call these SL2R gauge fields? The reason for that is that under local diffeomorphisms and under infinitesimal diffeomorphisms and local Lorentz transformations, these combinations transform exactly like an SL2R gauge field does under gauge transformations. And indeed, you can recast the Einstein-Hilbert action in terms of 2 copies of the SL2R Chern-Simons action for these gauge fields, with level K, where K is related to the central charge in a way that I didn't write down, but semi-classically, K goes like C/6. So the Einstein equations are simply the Chern-Simons equations, which tell you that A and A bar are flat connections. However, what I want to emphasize here is that the phase spaces of the 2 theories are importantly different. They're not the same. And I'll discuss the precise sense in which that's true in a second. So at least in this case, gravity is not a gauge theory. It is still different. And, of course, there are more conceptual reasons why this shouldn't be true, why gravity should not be a gauge theory. For example, in gravity, we gauge large diffeomorphisms. In gravity, we sum over topologies, whereas, Chern-Simons theory, for example, is a TQFT that you typically consider on some fixed background manifold, and it would be very unnatural to sum over topologies. and moreover, only local diffeomorphisms are gauged. Okay, so to define the phase space more concretely, let's consider the canonical quantization of the theory on some manifold that is locally like sigma times the reals, where sigma is some possibly punctured Riemann surface that you can think of as an initial value surface for the canonical quantization. So locally, we're thinking about configurations like this. Now, the gauge theory phase space on configurations like this is simply the moduli space of flat connections on sigma itself. So you can reduce it to a statement about the 2D gauge field on sigma. And what I want to drive home here is that most of these connections are in fact actually not good initial conditions for gravity. They would be correspond to very singular metric configurations in gravity. Now, at least in the case of SL2R times SL2R, this moduli space of flat connections is actually a disconnected space with a bunch of distinct components. And the gravity phase space is actually one of those components. So the gravity phase space is, in fact, given by two copies of the Teichmüller space on sigma. Now, what is the Teichmüller space? It's the space of hyperbolic metrics on sigma. You can also think of it as the universal cover of the moduli space of the Riemann surface. And it's a non-trivial theorem that precisely these gauge field configurations uplift to smooth 3D metrics on M. So they correspond to smooth hyperbolic metrics on sigma, but it's a non-trivial theorem that they can be uplifted to smooth 3D metrics on the full 3-manifold. This is due to work of Krasnov and others. Okay, so now that we've identified the gravitational phase space, in order to proceed to the quantum theory, we now have to quantize Teichmüller space. And this sounds very daunting at first glance, but thankfully this was carried out in an extraordinarily prescient paper by Hermann Verlinde in 1989. And this idea was later refined by Kasheyev and others. And what Hermann showed in his paper is that the gravitational phase space is given by two copies of this space that I'll call H of sigma. And H of sigma is simply the space of Virasoro conformal blocks on sigma, with the further restriction that all of the internal weights, so conformal blocks are characterized by some external, if you're considering some configuration on sigma with external operators, there's some external operators, but they should really think of them for the purposes of this talk as depending on the conformal weights of the exchanged operators in the OPE. And for these blocks to be normalizable, they have to lie above this black hole threshold, C-1/24. I'll discuss the precise sense in which this is true in a second. And what I want to emphasize here is that these conformal blocks are actually quite a natural family of wave functions on this Teichmüller space. In fact, this identification of the Hilbert space in terms of the space of conformal blocks is extremely natural from the point of view of holography. So the bulk partition function is some contribution to the full gravity path integral, which is supposed to be computed by the partition function of the boundary theory. And conformal blocks are, of course, the building blocks of CFT correlation functions on sigma. So this identification is at least intuitively very natural. Now, perhaps unfamiliarly, from the consideration of other TQFTs, you might be more familiar with, like Chern-Simons theory based on some compact gauge group. This Hilbert space is infinite dimensional, and that will lead to some subtleties in the theory that I'll discuss shortly. And just for the experts, these are precisely the same conformal blocks that appear in the conformal block decomposition of observables in Liouville CFT. So just a quick refresher on what conformal blocks are. As I said earlier, they're the kinematic building blocks of local CFT observables. So the way in practice that we compute correlation functions of local operators in CFT, as I told you earlier, they're completely solved in terms of the CFT data. So what we do is we consider a pair of pants decomposition of the possibly punctured Riemann surface sigma, and we insert a complete set of states in all the cuffs of those pair of pants decompositions. So that gives us a bunch of products of 3-point functions on configurations that are topologically like glued pairs of pants. So we get a structure constant for each of those pair of pants. And the remaining kinematic dependence, which computes the contribution of some exchanged operator OS and its entire conformal family, is given by the conformal block. So that leads to this kind of decomposition of the CFT observable, where you have the dynamical data of the CFT, these structure constants, times these conformal blocks, which are completely fixed by symmetry. Now, throughout this talk, I'll use this parameterization of the internal weights in terms of this variable called P. P is sometimes referred to as the Liouville momentum, and it's just a natural variable for Virasoro representation theory. In particular, P is real for this above threshold range of conformal weights. And here M is just some abstract label for the moduli of the punctured Riemann surface. Now, of course, the pair of pants decomposition is far from unique. You can do this in a bunch of different ways. So for example, for the 4-point function, here's the T channel decomposition. So we started in the S channel, 1, 2 to 3, 4. You can equivalently decompose it in this T channel, 1, 4 to 2, 3. And this involves a different set of CFT data. Now, the independence of these different pair of pants decompositions, locality of the CFT, amounts to some infinite set of non-perturbative constraints on this CFT data. And this, of course, goes by the name of conformal bootstrap. Now, I told you that we have a Hilbert space here for the gravity theory. And I told you about the vector space that's involved, which is the space of conformal blocks. But a Hilbert space is more than just a vector space. We need to propose some explicit form of the inner product on that vector space. And actually, that was also done in Hermann's 1989 paper. And one of the contributions of our paper from earlier this year was to give this a sort of modern reinterpretation. So let's unpack this a little bit. There should be a vertical line here. It's not showing up. Anyway, so the this conformal block inner product. So first of all, there's a lot to unpack here, so let's go through it. The conformal blocks are specified by a channel, so I specify that by this abstract label C. They're characterized by some set of internal conformal weights, which I label by P and P prime. These are bold because really there's a vector's worth of internal weights in general, 3g minus 3 plus n of them. So we're after some algorithm that takes two conformal blocks and returns a number. Now, the conformal blocks, like I said earlier, they're natural wave functions on Teichmüller space. So one thing you can imagine doing is integrating them over Teichmüller space. Now, in order to make this well-defined, you sort of treat the integrand as if it's a string theory integrand, because after all, Teichmüller space, the integration over Teichmüller space is locally the same as the integration over moduli space. So there's a Weil anomaly, because these conformal blocks have some central charge C. And we can cancel that Weil anomaly by coupling it to some auxiliary CFT with central charge 26 minus C. And I'm really only aware of one family of CFTs that exists for all values of the central charge, say less than 1. And that's this so-called time-like Liouville CFT, which is closely related to, but not equivalent to the analytic continuation of ordinary Liouville CFT. It's some distinct continuous family that exists for C less than 1. And then in gauge fixing diffeomorphisms, we also involve the BC ghost partition function or correlator here. Now, another thing is that suppose sigma has some punctures. So imagine these are sphere 4-point blocks, then there's some external weights. So the correlator that you couple to in time-like Liouville CFT will also have some external weights. And you choose those external weights to solve the mass shell condition so that they add up to 1. So that's the structure. This is an explicit form of the inner product. And as I've tried to emphasize, it's of course extremely suggestive of what we compute in perturbative string theory through worldsheet integrals. in computing like perturbative string scattering amplitudes, for example. There are some slight differences, and those differences are important, of course. Here we're integrating individual conformal blocks, which are not crossing invariant, so we have to integrate them over all of Teichmüller space for that integral to be well defined. Whereas in string theory, we integrate a full partition function or correlation function of the worldsheet CFT. And because those are crossing invariant, it's well defined to just integrate them over moduli space. But indeed, this conformal block inner product is intimately related to a worldsheet theory that we studied very recently with Lorentz, Beatrix, and Victor that we called Virasoro minimal string theory. There, you just replace the conformal blocks by the correlator and ordinary Liouville CFT with central charge C and integrate over moduli space. So I think if you're feeling uncharitable, I think you could interpret everything I'd said so far roughly as review. But one of the main contributions of our paper was to give a much more useful perspective or representation of this inner product. Again, this vertical line is missing in the PDF. That's funny. Okay, in the paper, we argued that this inner product is in fact orthogonal. So it's a delta function supported when all of the internal conformal weights are equal. And there's some overall weighting function here that we call rho. And we argued that it's kind of like a measure of rho is in fact given by the OPE density in Liouville CFT for the correlation function of Liouville CFT on sigma in the channel of the conformal blocks C. So this can be given a very concrete definition. So for example, you consider Liouville CFT on this genus 2 Riemann surface, do a particular pair of Pants decomposition, and then on each cuff, you get a factor of the inverse 2-point function of Liouville CFT, which in this normalization we call rho 0, which is actually the same as the Cardy half of the chiral half of the Cardy formula. And then for each pair of pants, you get a factor of this C0 object, which is the DOZZ formula for the structure constants. And it's related to this variance in the Gaussian ensemble that I described earlier. So we argued from this from a few different points of view in the paper. Most importantly, I think, was consistency of this inner product with crossing. But there are also various arguments that more directly connect to bootstrap considerations and like the uniqueness of Liouville CFT as a diagonal solution of crossing, and from 3D gravity more directly. So this is some very explicit form for this conformal block inner product. And so I told you earlier that this Hilbert space requires all the internal weights to be sufficiently heavy above this black hole threshold. And that's because otherwise this integral over Teichmüller space might diverge. So in particular, the identity block, which plays an important role in 3D gravity, and indeed all blocks involving the exchange of any subthreshold operator are non-normalizable states in this Hilbert space. So that's okay. Some of them will show up and will play a role, but they won't have a well-defined inner product in this Hilbert space. Okay, so yeah, just to make this even more concrete, let's write down an explicit formula for this inner product for the case of sphere 4-point blocks. So these are two sphere 4-point blocks in the S channel. The only difference is they have different internal weights propagating in this internal channel. So this inner product is given by some delta function that sets these two weights to be equal, divided by this explicit combination of rho 0 and C0. So this is just the OPE density of the 4-point function of Liouville CFT. Now, we have even more, in fact. In fancy language, this conformal block Hilbert space supports a projective unitary representation of the 2D mapping class group. And basically what that statement amounts to is the fact that conformal blocks transform nicely under a pair of Pants decomposition or crossing transformations. So for example, you can take a block in the T channel and expand it in a complete basis of blocks in the S channel with some crossing kernel appearing And so two things to highlight. One is that this integration range is over the space of normalizable blocks that I discussed earlier, the ones that furnish the Hilbert space. And this crossing kernel F is actually explicitly known, despite the fact that the conformal blocks themselves are not known, which is kind of a crazy and remarkable fact. So the whole point is that this inner product that I wrote earlier is actually preserved under these crossing transformations. And this is one of the ways that you can derive this form of the inner product. So the upshot is that the Hilbert space closes under crossing, and the quantization of the phase space is independent of the basis of conformal blocks that you choose. So what that means is that we have enough data to define a consistent TQFT. So let's take stock. We started with 2 copies of SL2R Chern-Simons theory on this class of manifolds that locally looks like sigma times R. By the way, the restriction to this focus of manifolds was just so that we can do the canonical quantization. Then we made what, from the gauge theory point of view, surely looks like a very arbitrary restriction on that phase space. And then we decided just to quantize that one component that we restricted to. So this was the Teichmüller component of the gauge theory phase space, which corresponds to hyperbolic metrics on sigma. There's no reason that that has to give you something consistent a priori. But we went ahead, quantized Teichmüller space, and landed on this Virasoro TQFT. So this is some TQFT whose Hilbert space on sigma is the space of conformal blocks on sigma. And this defines a consistent TQFT, although there are some subtleties associated with this infinite dimensional Hilbert space. I'll probably discuss them now. So although it's well defined, as I've argued, this Virasoro TQFT is in some respects a kind of unconventional TQFT. And the reason for that ultimately boils down to the infinite dimensionality of the Hilbert space. So you have this continuous spectrum of Wilson lines. Nevertheless, it satisfies essentially all of the usual TQFT axioms, for example, those based on modular tensor category, except that its spectrum does not contain the trivial line, which is kind of weird. But this is related, of course, to the fact that the identity block is not a normalizable state in the Hilbert space. So what this means is that if you're not careful and you just sort of blindly apply some surgery techniques, perhaps familiar from Chern-Simons theory, you can sometimes run into divergent or otherwise ambiguous or ill-defined results. So for example, the partition function on the 3-sphere, which is not a hyperbolic 3-manifold, in these TQFTs based on rational or modular tensor category is given by the identity component of the modular S matrix. But this is ill-defined here because for us, the identity never appears on the right-hand side of these crossing transformations. So basically what this means is that you can still apply surgery techniques, but you just need to be careful that you only cut along surfaces for which this Hilbert space is well-defined. In other words, along hyperbolic surfaces. So to summarize, we have some concrete TQFT that we call Virasoro TQFT, and it's related to Liouville CFT in precisely the same way that group G level K Chern-Simons theory is related to the corresponding WZW model. The Hilbert space is the space of conformal blocks. It's just now that this is a continuous space, whereas in here this is some finite discrete space of GK Casimudi blocks. Okay, so now let's get our hands a bit dirty. Actually, before I go on to the applications, let me ask, are there any questions so far about this construction? Okay. So now that we have this, this concrete TQFT, its role in life is to compute partition functions on 3 manifolds, as far as I'm concerned. So, for example, suppose you're considering a hyperbolic 3 manifold with boundaries. And suppose you have some you know, multiple boundaries given by this disjoint union of surfaces sigma. Then I want you to think of the partition function on M as a sort of vector in the tensor product Hilbert space that's associated with each of these asymptotic boundaries. So this partition function is some state in this tensor product Hilbert space. So in this case, you have 4 copies of the 3-punctured sphere Hilbert space. This may be a bad example because that Hilbert space is only has a single state. But more generally, that's how I want you to think about the partition function. So in practice, what do? Well, as usual in like Chern-Simons theory, we compute the partition function using surgery techniques. So we take the 3-manifold and cut it through the bulk into 2 smaller pieces, M1 and M2. So for example, we'll talk more about this example a little bit later. Here's this 4-boundary wormhole where each boundary is a 3-punctured sphere, and I can cut it through the middle along this 4-punctured sphere. So the partition function on each of these 2 pieces you can think of as a state in this cutting surface Hilbert space. So to compute the partition function, you simply compute the inner product of those states in the Hilbert space of this cutting surface. So the general prescription, like how this works in practice, is we do surgery through the bulk, cut along some surface. That will give us some state in the Hilbert space associated with the boundary components of that half and the splitting surface. You determine the state in the splitting surface by inserting some complete set of states on the other boundaries, and then take the inner product. And the main tool that we used is this concept from topology called Heegard splitting. And it's easiest to describe for closed 3 manifolds, so I'll do that in what follows, but in the paper we showed that there's straightforward generalizations of this in the presence of asymptotic boundaries or Wilson lines. So it's a non-trivial fact that closed 3 manifolds, they don't even have to be hyperbolic, admit a Heegard splitting into 2 handle bodies, which I call S of sigma. So what is a handle body? You take some boundary Riemann surface and fill it in the bulk along some cycles. Now, to form the 3-manifold, you then identify the boundaries of those 2 handle bodies up to some modular transformation acting on the boundaries. So up to some action of the mapping class group of sigma acting on one of these boundaries. This boundary is known as the splitting surface. Now, this may not seem very intuitive. I know when I first heard about it, I didn't really have a good intuition for it. But one way to think about it is from the point of view of the triangulizability of 3 manifolds. So 3 manifolds admit triangulation often into tetrahedra. So you take some triangulation of the 3 manifold, and then you thicken it, the skeleton of that triangulation, very slightly. That defines a handle body. If you just try to visualize it in your head, that will become clear. And then the closure of the complement of that thickening, just like the thickening of the dual skeleton, is also a handle body. And they're identified along their boundaries, which is exactly this Heegard splitting. So the upshot is that you can decompose closed 3 manifolds into these 2 handle bodies, which are glued along their boundary up to some relative modular transformation. Now the TQFT partition function on each handle body prepares a special state in this Hilbert space. While it's actually not a normalizable state, as we discussed earlier, it's the identity block, which you can see from like the cojoint orbit quantization of Virasoro. This is also a familiar fact from the Chern-Simons WZW model correspondence. The partition function on the handle body creates the identity block in the Kac-Moody algebra. So the upshot of that discussion is that the partition function on M is then given by the expectation value of this representation of the mapping class group element in the states prepared by these identity blocks. Now, I told you earlier that the identity block isn't a normalizable state, and that's true. So what that means is that for example, if you take phi to be the identity element, this inner product clearly diverges. And heuristically, this expectation value is finite whenever phi is sufficiently complicated. And we expect that it's finite whenever m is hyperbolic. And this is held up in examples we've studied, but we don't have a proof that, this is always finite for m hyperbolic. And you could even imagine that it's finite in some situations, even though m is not hyperbolic. So understanding this better is something we would like to do going forward. Okay, so this TQFT partition function is a priori defined on a fixed topology. On the other hand, the gravity path integral involves the sum over topologies. So there's this mapping class group here of the bulk manifold. I label it by both the 3-manifold M and its boundary components because I wanted to preserve the boundary components. So this is the space of large diffeomorphisms. And this sort of captures the mismatch, if you want, between the gravity and the TQFT gauge groups. Now, there are also large diffs that purely act on the boundary components. And these are captured by the mapping class group of the boundary components. And these should be included in the sum over topologies. So our proposal for the gravity path integral on this equivalence class of 3 manifolds, if you want, which are related by mapping class group transformations, is the square of the TQFT partition function. So because remember, gravity is related to 2 copies of this TQFT. So you square it, and then you have to sum over the mapping class group transformations that act on the boundary. And you have to gauge out by the bulk mapping class group, which you can actually promote to some subset of this boundary mapping class group, because the TQFT partition function is already invariant under those transformations. So this is the proposal. It doesn't capture all of the sum over topologies. We'd want to sum over all topologies with boundaries given by partial m, but this is at least some contribution to the gravity path integral with given boundary components. And the conjecture is that this TQFT partition function is finite whenever m is hyperbolic. In other words, corresponds to a solution of Einstein equations in ADS3. And this indeed checks out in the examples that we've considered, but we don't have a proof. Okay, so in the remaining 15 or so minutes, let's discuss some explicit examples just to show the utility of this technology. So I think the simplest example is the Euclidean wormhole. This is this 2-boundary configuration that I drew at the very beginning, topologically equivalent to sigma times an interval. And this is actually a kind of trivial state in the TQFT. And the reason is that you can imagine cutting open some other 3-manifold along this cutting surface sigma. You glue in the Euclidean wormhole, and you haven't done anything topologically. So it amounts to the resolution of the identity in this boundary Hilbert space. So you can compute it by inserting this complete set of states, rho, and then you have the conformal block on each of these boundary components. And then if you fix the moduli of these boundary components, so take the expectation value with some states of fixed moduli, M1 and M2, in these conformal blocks, and this actually computes the Liouville CFT partition function on sigma, but with the moduli paired up in a funny way. So normally we would have M and M bar here, but here we have M1 and M2. And if you square this, this actually agrees with this average product of CFT partition functions in this Gaussian ensemble that I mentioned at the beginning. So this is some strong consistency check or compatibility of these two proposals. Now, of course, the full gravity partition function will include a sum over relative crossing transformations. So let's apply this formula in this specific case. Now, the boundary mapping class group is, of course, just given by 2 copies of the mapping class group on sigma. So we sum over 2 copies of the product of these mapping class groups a priori, but we have to gauge out by the bulk mapping class group. And in this case, this is just the diagonal mapping class group that acts simultaneously on the two boundary components. So that quotient gives you this sum over this relative mapping class group, where you view the crossing transformations as only acting on one of the boundaries. For the experts, this has a very precise similarity to the proposal by Collier and Jensen for the double torus wormhole, where each boundary is a torus. There's some details in what you might call the TQFT partition function, but it's okay because that configuration is not hyperbolic, and so strictly speaking, it's outside of the scope of this TQFT. But the structure of the sum over relative crossing transformations of some seed is exactly the same. Good. Let's discuss a slightly more non-trivial example, although in some ways it's simpler because the boundaries are just three-punctured spheres. So let's discuss this four-boundary wormhole, which is this configuration with four boundaries that are each a three-punctured sphere, and we have these defects in the bulk in this sort of tetrahedral configuration. Now this controls the leading non-Gaussianity in this ensemble of CFT data, and so you might expect that this the gravity partition function on this wormhole corresponds to some fourth moment of the CFT structure constants, basically where you get a C for each boundary component here. And this is relevant. This is, in fact, needed for internal consistency of this whole story. It's just so that when you compute quantities on the CFT side, you get the same answer no matter which channel you expand it. And indeed, these are the structure constants that appear in the S channel and in the T channel of, say, some 4-point function. However, I know of no way to compute the gravitational action of this thing in the metric formalism. I don't even know how to begin to write down like a metric on this thing. But with the TQFT, it's actually extremely straightforward. So the way we do it in practice is by applying this Hegardt splitting technology that I told you about earlier. So we cut through the bulk along this, what is now a four-punctured sphere. So 1, 2, 3, 4. Each half produces some state in this four-punctured sphere Hilbert space. So you get some conformal block in this, some sphere 4-point conformal block from each half. So the gravity partition function is given by the inner product of these two states in the four-punctured sphere Hilbert space. So we can compute this inner product and get some answer. We square it, and that gives us the gravity partition function on this four-boundary wormhole. And what we get is a square root of the variance for each boundary, 1, 2, 3, 4. So this is that C0 object that showed up earlier, times this funny quantity, which is the Virasoro 6J symbol. It's in fact proportional to this fusion kernel F that I wrote down earlier in the talk. And this object is known to have some tetrahedral symmetry, which is of course obvious from the bulk configuration of Wilson lines. And indeed, if you study the semi-classical limit of this thing, so take C very big and scale up the conformal weights in a particular way, then I forgot the citation here. What Teschner and Vardanov showed is that this actually exponentiates to the volume of a particular hyperbolic tetrahedron. And so this is quite suggestive, and it will become even more suggestive in the other examples that I'll describe. So you can go on and compute higher moments of CFT data in this ensemble by considering higher multi-boundary wormholes. So here's a simple example where you take 6 boundaries, again, each of which is a three-punctured sphere, that corresponds to some 6th moment of the CFT data. Now you can cut through the bulk, again, as before, but this time you can, in fact, only cut along a three-punctured sphere, which is quite nice. And in fact, each half is topologically equivalent to this four-boundary wormhole that I discussed earlier. It may not be obvious from the picture, but if you think about it for a little bit, it becomes clear. So you have the state in the three-punctured sphere Hilbert space. You compute this inner product, and what you get, you compute the inner product and you square it, and what you get is, again, a factor of the square root of the variance for each boundary component times two 6J symbols, roughly one for each half. And this corresponds to this sixth moment of 6J symbols. And of course, what this means is that in the semi-classical limit, you just get the sum of the volumes of the hyperbolic tetrahedra corresponding to each half. In fact, even at the level of 6 boundary wormholes, you can consider more complicated configurations just by arranging the defects in a slightly different way. So here's a slightly more non-trivial one where you have this sort of Yang-Baxter-like configuration of the Wilson lines. You split along these 4-punctured spheres. Now you're splitting along 3 4-punctured spheres. You could do it differently. You could split, say, down the middle through this way along some 1, 2, 3, 4, 5-punctured sphere, and you get the same answer. But what you get is, again, a product of the square root of the variance for each boundary component times this integral over 3 6J symbols. And this corresponds to this sixth moment. And all of these results that I've told you about so far are needed for consistency of this ensemble description, where you take some, for example, product of 3 4-point functions or 2 5-point functions. It corresponds to the different ways to split this thing in this Gaussian ensemble. And so the simplicity of these results and actually their precise form suggests that there might be some very simple diagrammatic rules to compute arbitrary statistics of CFT data. And those rules are essentially identical to the Feynman rules for this JT gravity plus matter theory recently studied by Jafferis, Kolchmeyer, and collaborators. Moreover, the relation to the 6J symbol and the hyperbolic tetrahedron suggests that there might be some more simplicial way of thinking about 3D gravity that is so far belied by this TQFT construction. Okay, I have a few minutes, so let me just conclude with a kind of cool example. So you can really start to go wild with this stuff. You know, these partition functions are supposed to be topological invariants, and you know, the space of hyperbolic 3 manifolds is a kind of crazy space. But one family that you can consider is hyperbolic links or knot complements. So this is where you take a knot embedded in S3, and then the complement of that knot in some situations defines a hyperbolic 3 manifold. And the simplest and sort of most classic example is this figure-8 knot complement. So I embed this figure-8 knot into S3, and then the complement is a hyperbolic 3 manifold. And you compute this basically the exact same way we compute everything else. You cut through the bulk along some surface, maybe do some crossing transformations, and then take the inner product. So here I cut along some 4-punctured sphere. This defines a state corresponding to the interior and one corresponding to the exterior. I do some crossing transformations just to make it more interpretable, and then take the inner product. And what I get is this formula involving an integral over the 6J symbol. And what's amazing is that in the semi-classical limit, where you take c to infinity, this indeed exponentiates. So this very complicated formula involving this integral of the 6J symbol. And there are, in fact, other representations that you can use by computing, like cutting into some different way. But in the semi-classical limit, you find this volume of this figure-8 knot complement, which is some very explicit number, which is, I think, very cool. But of course, the implications for holography are very unclear because there's no asymptotic boundary. All right, so let's wrap up. I've told you today about a proposal for ADS3 quantum gravity on arbitrary hyperbolic 3 manifolds in terms of this TQFT, which is, I think, well-defined, but perhaps has some unfamiliar features. This TQFT was defined by quantizing Teichmüller space. Now, this leads to a very, I think, concrete and explicit prescription to compute partition functions, at least at the level of fixed topologies in 3D gravity with more or less standard techniques from TQFT. And what I've tried to convince you of is that this trivializes, or at least simplifies, many computations that were either a real pain in the metric formalism are just not possible. And moreover, these calculations at the end make much more manifest the relation with the CFT ensemble description of semi-classical 3D gravity. And I didn't emphasize it, but these results all hold at finite central charge. However, of course, the restriction to a given topology at finite central charge is not really a sensible thing to do. But at least this correspondence between the average CFT quantities on one hand and the 3D gravity partition function on the other at the level of a fixed topology that is extended beyond the semi-classical limit is what we see. So optimistically, hopefully this technology will help us determine the extent to which any version of pure 3D gravity makes sense at the quantum level. So there are, I think, many interesting things left to understand. So I just described the fact that the relationship between the gravity partition function and average CFT quantities has been extended. And this really begs for some unifying description. And I think some important steps towards that were made in this recent paper by Bellin and collaborators. There's the question of the finiteness of the TQFT partition function. We would like to prove that it's finite whenever M is hyperbolic. It holds up in the examples we consider, but we don't have a proof in general. I mean, we would love to understand non-hyperbolic three manifolds. These are believed to be important in some situations, believed to give important contributions to the gravity path integral. And so there may be some situations in which our prescription gives finite answers, but even if that's the case, there's still the question of interpreting them. So a natural target would be these Seifert manifolds with torus boundary that were described in the paper by Maxfield and Toriachi in 2020. So we saw some examples of this volume conjecture. It would be nice to prove it. So here, if M has asymptotic boundaries, then you have to talk about the renormalized volume. And you can even imagine a one-loop refinement of this volume conjecture that includes this contribution from the Selberg trace formula. More generally, so I talked a lot about the contribution of a given topology, but our experience from the torus tells us that it's sometimes non-trivial. The sum over topologies. When does the sum over hyperbolic topologies make sense? Now, for closed hyperbolic manifolds, they're ordered by their hyperbolic volume. And you might imagine trying to sum over closed hyperbolic manifolds, but there are accumulation points in the spectrum of volumes. But arguably, those can be dealt with using similar regularization techniques as those introduced by Maloney and Witten in the context of the torus partition function in 2007. Now, this sum is probably, presumably asymptotic. And so one might, if one could get a handle on that, perhaps one might learn about yet further non-perturbative effects, sort of like doubly non-perturbative effects in gravity. At the end, I hinted at some relation with these simplicial models, where you triangulate the three manifold and then do some state sum involving 6J symbols associated with the tetrahedra. It would be nice to understand this. In fact, we started out when we studied this theory trying to formulate it as a sort of Triaviro style TQFT, but there were technical complications and we didn't succeed. And obviously, it would be really important if there's any way to extend this to positive cosmological constant and formulate DS3 quantum gravity. The naive generalization of what I told you doesn't work because of technical differences between SL2C and SL2R times SL2R. But I think this would be very important to understand. But we have to leave that to the future for now. So thank you for your time. Not obviously, yeah. I think they're a priori independent. We sort of stumbled on this phenomenologically. But yeah, because that involves like SL2C Chern-Simons theory, and this involves this funny TQFT, which is like a quantizing a particular component of SL2R times SL2R. Um, there's no obvious relation between the two, but it seems to check out in the examples we've considered. Thanks for the question. Um, yeah, right. That would, in SU2, that would mean you associate some particular representation to these not complement. Yeah, to be honest, we haven't really thought about it. We always consider the case of the cusp. This is like having p equals 0. This Wilson line has Liouville momentum p equals 0. But yeah, we have, to be honest, we haven't really thought about that, but it would be interesting to understand better. Yeah, we didn't really discuss it. I guess the solid torus is on slightly different footing. Um, yeah, a priori it's different. But let's see, I wrote down this naively. So if you follow this prescription to compute the partition function on the BTZ, on let's say with boundary torus, the contribution of the BTZ black holes to this configuration, then the TQFT partition function on the solid torus gives you the identity character. The mapping class group of the boundary is just SL2Z, and the mapping class group of the bulk is this Z component, and sometimes referred to as gamma infinity, but it's the set of Dane twists where you cut open the solid torus and do some rotation by 2 pi and then glue it back in. The identity character is invariant under that, so you mod out by those. And of course, that just leads you to the Maloney-Wooden prescription, which we know for the experts in the room know that leads to slightly nonsensical answers. So this is why I did not want to downplay the role of off-shell configurations in 3D gravity, which are believed to fix this issue. It's just slightly beyond the scope of what we were able to work out in this project. But if you did follow your nose and follow the prescription we laid out here, it would lead you to the Maloney-Wooden answer for the torus partition function, which is known to have issues.